Now let's talk about stellar aberration. Remember the key background here is that the Michelson-Morley experiment, the goal of which was to detect the influence of the ether wind on the speed of light, came up with a null result. And one very surprising result, one possible explanation for that surprising result was that maybe somehow the Earth dragged the ether along with it as it went around the sun. So that there would be no ether wind, no ether breeze that could be felt, in this case by light, at the surface of the Earth. But there were other experimental results that argued against that possibility. And the one we want to talk about is called stellar aberration. Here's the basic idea. We have two cases. The first case is with the Earth moving around the sun, okay, with some velocity v, about 30,000 meters per second actually is what it is. So a fairly large velocity, although fairly small compared to the speed of light. And let's say we have light from a star. So let's say we have a telescope at the North Pole or someplace up close there, and we're looking at maybe the polar star or some star in that vicinity. So light essentially is coming straight down here towards the Earth, while the Earth is revolving around the sun this way at the velocity v. So if and this light wave is going to essentially follow through a path through the ether here, this vibration, the supposed ether. And if the ether is dragged when it gets near the Earth, then everything just gets shifted along with it, including the path of the light through the ether. Okay? You have to imagine that if the ether is the background here, and this is traveling through the ether, then if the ether gets shifted along with the Earth, as the Earth goes with velocity around the sun, then the path of that light beam is also just going to get shifted with everything else. So that in that case, as the telescope gets shifted with the velocity v, the Earth, of course, is going with velocity v, the telescope on the Earth, velocity v. If the ether also is going with velocity v, being dragged by the Earth somehow, then this light beam is going to have in this case, a rightward shift at velocity v, and will just fall straight down in the telescope. The telescope is here, it moves over here, but meanwhile, the whole ether is also shifted the path of the light beam, so it just matches up with the telescope, so that when it actually gets to the telescope here, it will just go straight down the telescope tube and hit the bottom. Now, if we were watching this from sort of outside, as it were, we would sort of see it trace out a path like this, because at this instant, the telescope is here. When the light actually gets down to here, of course, things get moved over here. So the actual path, if we were an outside observer from space, watching Earth go by and watching the starlight come down and then sort of get into the region of the moving ether, the path would be something like this, because this is where the telescope would end up over here at that point. But as far as observer on the Earth is concerned, since they're moving with the telescope, everything, the starlight just comes straight down and follows the moving ether, follows the moving Earth, and we don't have to do anything with the telescope. We just point at the star, and it works fine. Well, what a person named James Bradley found out all the way back in the 1720s, he's an astronomer, and what he actually was trying to do was determine the distance to stars using an effect known as parallax, that if you take a measurement of a position of a star, say in June, and then wait till the Earth has gone 6 months around the sun to December, say, and take a picture of the same star, it should shift slightly because, first you're over here, and then you're over here, and the star's up there. If you take the photographs, maybe there'll be a slight shift in the direction of it. Turns out, actually, the stars are too far away to be detected that way in terms of the equipment that Bradley had. But what he did find was that, yes, you do actually have to shift your telescope slightly at a slight angle to catch the starlight coming down properly. And so that's case 2 here that we're going to explain, where we're assuming the ether is not being dragged by the Earth. Okay, so in this case, here's the star again, here's Earth. Earth moving that way, the telescope moving that way as well. Since there's no ether drag here, the ether is not moving with the Earth, so the path of the starlight is just going to be straight down here. It's going to end up right at that spot. But by the time it gets to that spot, Earth has already moved over here. Unlike in this case, the moving ether, the ether being dragged, drags the starlight along with it, and therefore the starlight ends up where this telescope does a few moments later when it's over here, a few seconds or even less when it's over here, say. In this case, the ether is not being dragged, so the starlight comes straight down, and if it's aimed at the telescope at this point, say about to enter the telescope, a few milliseconds later, the telescope has moved a little bit over here, and the starlight will miss the telescope. So here's what you actually have to do, and I've tried to diagram it via 3 snapshots of the light going down the telescope. And by the way, maybe a real world, well, this is a real world example, but an everyday life example, this would be an umbrella and raindrops. If the rain is coming straight down, and yet you're walking briskly or running through the rain, you have to tilt the umbrella to catch the rain that is falling in front of you, because otherwise you will run into that rain as you go along. Same idea here. We have to tilt the telescope to catch the starlight coming down. And because the starlight's going to end up at the bottom when we're over here, we have to catch it earlier on. So this is like 3 snapshots, A, B, C. So we catch the starlight coming down just as it enters. We'll say a second later. It's much quicker than that, of course. But a brief instant of time later, the light has come straight down. So it's going straight down. And it's going to end up, you see, this is where that starlight is going to end up, right there. But if we had positioned the mirror at that point, then it hit the side of the telescope coming down. So we've got to have it just enter the telescope here. Millisecond later, or microsecond even, the light, even a nanosecond probably, the light is halfway down the telescope tube. The mirror is coming over into this position, but not quite there yet, so it's moved a little bit. And then finally, when the light gets down to the bottom of the telescope is moved far enough so that it catches it just right. So again, sort of the umbrella and the raindrops idea. You've got to tilt the umbrella a little bit to catch the raindrops that are falling down in front of you. Same thing here. You have to tilt the telescope so it catches the light coming down just at the top of the telescope, and then as the telescope moves, it catches the light beam at the very end there, the bottom of the telescope. So that's the idea with ether not being dragged. Again, the starlight's coming straight down because the Earth is moving, and ether is not being dragged. The starlight is not going to be shifted over. You have to shift the telescope slightly at some slight angle. So you might ask, actually, what is this angle? You can call this angle right here alpha. So that's the angle of tilt. You can do an analysis. It's not that difficult. We won't do it. We'll just state the result. Turns out that alpha more or less goes like the velocity of Earth. So we'll say v Earth here around the sun. So again, about 30,000 meters per second, divided by the speed of light, which is 300 million meters per second. I think that's a difference of about 10,000 times there, or something like that, if I did that correctly. But a small number. So alpha turns out to be actually about 0.012 degrees. I think I got the right number of zeros in there. Very small angle. So this is greatly exaggerated here. It's just a slight tilt in the telescope in this situation. But it was clear evidence that the ether was not dragged at the surface of the Earth. So then you had a problem. You had experiments like stellar aberration and some other results too that indicated there was no ether drag at the surface of the Earth. And then you had experiments like the Michelson-Morley experiment that was showing no ether wind at the surface of the Earth. Therefore, how do you explain that? Well, maybe ether drag, and yet it can't be drag because you have experiments like this as well. So it was a big puzzle, big conundrum. And so in the next video lecture, we'll actually look at some of the so-called ethereal solutions that people came up with in terms of how to explain the null result of the Michelson-Morley experiment, what might be going on, and then we'll also consider Einstein's solution to the problem.